Hello, everyone. Thank you for having me. My name is Arjun Dabas, and I'm from Beyond Space Technologies. Currently, I'm giving this presentation from the Moon Mars habitat while being in a simulated environment. Here, I'm going to be presenting the simulating circadian rhythm disruptions and cognitive performances on astronauts using a machine learning model. The name is a mouthful, but it's pretty unique. All right, so to introduce it. As you know, that astronauts in space, they lack natural cues. Like there's rhythm disruptions, there's reduced performances because it's a entirely desynchronized environment. There's no daylight or night light. There's sensory deprivation and initial weightlessness effect on the sleep quality as well due to microgravity and other reasons. As you know, there are multiple factors affecting sleep, as my colleague here, Pavana, presented in her presentation. There is stress, motion sickness, environmental stress, high workload, obviously, because they're astronauts, abnormal work, there's thermal discomfort, noise, and obviously, microgravity has a number of numerous effects on your health. There's also confined space, as you can get an idea from here. There's hypoxia and crew dynamics. There are also unsuitable sleeping bags, and there's absence of day-night cycles, and obviously that all affects your mental health, hence disrupting your circadian rhythm. Right. Now, there are few existing solutions to this problem. There are sleeping bags which monitor your biometrics. There's light therapy, as Pavana's presentation was about that. Then there is an active watch, but there's no feasible solution, all-in-one solution for that. They are still in testing module. Right. So there are now research gaps in it, as I said. There's no personalized medicine. There are variable biosensors. Yes, there's continuous health monitoring on board with multiple systems. There is genome markers in space, and there's integrated healthcare devices. Right. So as you can see on the right hand side, there's a circadian clock gene which regulates over here. Okay. Now here we have a methodology. Right. So as you must have known till now that it's a very tedious process to monitor everything, and there's a whole lot of data to be processed. That's where ML comes in. So we develop a ML based framework to classify the sleep quality and provide a personalized circadian rhythm optimization because each body is different and they adapt differently. We optimize sleep quality through HRV metrics of astronauts. Actually, we are currently testing it out in this habitat over here. I have this EEG machine lying around. We monitor and identify features affecting sleep quality. So this is what we are doing. We get the data, then the data set transfers into HRV metrics, machine learning, and then sleep quality gets improved. Hence, the performance also improves. Now, the focus is on the HRV feature extraction as biomarkers reflecting ANS activity and sleep regulation. You can see on the graphs on the right-hand side. There, there are challenges like there's a lack of physiological data. So hence, we are currently going through the simulated environments, analog environments. But we have a probability region derived from mean and SD of real astronauts and HRV using Gaussian bell curves plot, which are reliable because that's where we got the data from. These are the bell curves on the right hand side, as you can see. Okay. Now coming on to the machine learning model, we have utilized three models, which is a random forest classifier. It handles nonlinear features such as interpretable, robust to overfitting. Then it rationalizes for inclusion. It identifies key HRV features and it's reliable for real-time use. That's one of the main features for it. Now, coming on to the gradient boosting classifier, it's highly accurate and it captures complex patterns for the data set. Because obviously there are going to be a lot of complex factors and there are numerous factors which affect your sleep and hence gradient booster comes in. It models subtle HRV interactions for strong generalization. Right. Now, third, coming on to the RBF kernel, that is a support vector machine, it works in high dimension space and it's robust to noise. It provides a stable classification under data variability. So now these are the results we have achieved. The random forest classifier has achieved a 78.2% accuracy, and the Gaussian is reliably captured variability across DF1 to DF3 stages, and output categories mapped into sleep quality labels as poor, fair, good, excellent. As you can see on the map here, they have precision as red, recall as blue, F1 scoring, and this is the accuracy for the three different machine learning models we have over here. And we have the HF component, which is elevated, same as in the good, excellent sleep, and the markers of parasympathetic activity in deep sleep. Then we also have the LF-HF ratio, which lowers in the good, excellent, but higher in poor and reflects in sympathetic and parasympathetic balance. So these are the features and sleep quality categories we have over here. Okay, so but there are some limitations as I was presenting earlier. There is a scarcity of real astronaut HRV dataset because it restricts general stability. There is synthetic augmentation. We relies on the Gaussian-based synthetic samples. And we also have model generalization. Performance varies when applied to real world. It's similar to the ideal world and the real world scenario. There's a heterogeneous astronaut populations, and obviously there's lack of clinical variation. So that's what our next step would be. We have the models ready, so we would like to test them on the real data sets once we achieve them over time. Hence, they would be eventually improving the sleep quality and the cognitive performances of astronauts. The sleep quality, as I said, sleep quality classifications are not yet cross-verified with polymorphography or medical benchmarks. Okay, so there is a future scope to it. Because this is just the initial stage to it. We propose a design, a wrist-worn system with ML because that measures your movement. Now, that would not take as much of space and would also give us the data we require. Now, there is a personalized recommendation engine to adjust nap timing and your crew tasking sequence. As we have over in our habitats, we are designated 1 hour of nap time during the day in order to see how our sleep and our systems monitor. We also have personalized medicine to tailor your fatigue management and mapping individual sleep immune performances. But medicine would take a bit of time because each person reacts differently, so that needs a bit of testing. There is Bayesian risk modeling to predict the likelihood of alertness, lapseness, or performance drops in long-term missions. And that brings me to the end of my presentation. I did not go much into data sets because it's just pretty deep to if I go into that. So I am just going to wrap up over here. I'm open to any questions and thank you for the presentation.